Let's consider the chapter on calorimetry. Today we are going to consider the concept of what is heat and what is temperature. How does this temperature or this quantity of heat is going to affect our day-to-day life? What are the after effects of using heat? Or what are the after effects of rise in temperature, fall in temperature? What happens when a hot body is kept near a cold body? And so on. This chapter of heat or calorimetry has got certain prerequisites. Talking about the prerequisites, as I said, we should know what is heat. Heat is nothing but the total content of kinetic energy that is present in the substance. Whereas as far as temperature is concerned, we talk about the sum total of kinetic as well as potential energy. Then we should know what are the units which are used to determine the heat content or the temperature content. The heat content is normally measured in terms of joule, calorie or erg, whereas temperature can be measured in degrees Celsius, Kelvin or Fahrenheit. As far as discussion of 10th standard is concerned, we restrict ourselves for temperature only to degrees Celsius and Kelvin. Going on to the theory concept, talking about calorimetry. Calorimetry is that field of science which deals with the heat content of a body. When we say that a particular body contains certain amount of heat, or we say that a body has certain amount of thermal capacity. When we talk about thermal capacity, we define thermal capacity as the amount of heat required to raise the temperature of entire mass of the substance through 1 degree C. So when we say thermal capacity, it basically is related to the entire mass of the substance. However, when we divide this by the total mass, then we get the quantity as specific heat capacity. So we define specific heat capacity as the amount of heat required to raise the temperature of unit mass of a substance through 1 degree C. To be very specific in this case, we put it as 14.5 degrees C to 15.5 degrees C. The unit of thermal capacity is joule per degree C or joule per K, and the unit of specific heat capacity will be joule per kg per degree C or joule per kg per Kelvin. Remember here that we are not going to say degree Kelvin because that's not the right convention. When we put across Kelvin, it is always said as per Kelvin and not per degree Kelvin. Then coming down to the concept of principle of calorimetry. To understand this concept of principle of calorimetry, we keep two bodies, one hot body and one cold body, in the vicinity of each other. Say for example, I have ice cream and here I have a hot substance, maybe like a burning flame. So when I keep these two bodies into thermal contact, remember the word thermal contact, it is in physical contact of the two substances. We see that the hot body is going to radiate certain amount of heat. When this hot body is radiating certain amount of heat, ice or the ice cream that is present over here is going to gather or absorb that particular amount of heat. So the amount of heat that is being given out by the hot substance will be equal to the amount of heat taken in by the cold substance. This heat transfer continues so long as both attain a steady state temperature. This state at which steady state temperature is attained is called as the state of thermal equilibrium. So we have the principle of calorimetry that is applicable to a state of thermal equilibrium as when two bodies are in thermal contact, heat lost by hot body is equal to heat gained by cold body, provided no heat is lost to the surroundings. Now this gives you a recap wherein we say that this is in accordance to law of conservation of energy, because even law of conservation of energy states a similar statement. Energy can neither be created nor be destroyed, it only can be transformed from one form to another, such that the total energy of the system remains constant. So here also we are saying that the heat has been given out by the hot body, heat has been absorbed by the cold body, so that no heat is lost to the surrounding. Using the principle of calorimetry, we have one set of numericals. When we talk about numericals, we have numericals that are based on principle of calorimetry, wherein we use the relation, the amount of heat that is given or the amount of heat that has been absorbed is equal to mass into specific heat capacity into rise or fall in temperature. Using this relation, we can definitely solve sums that are based on principle of calorimetry. Now these sums that are based on principle of calorimetry are divided into 4 types. Just to make it simpler for you, we have categorized these numericals into 4 types. The first one is you have a glass beaker containing cold water. You're adding to it hot water. So you have cold water in the beaker and you're adding hot water to it. Then they ask you to find out the final temperature of the mixture. So in this case we can say, by principle of calorimetry, heat lost by hot water is equal to heat gained by cold water. Now since both the substances are same, we have mass into specific heat capacity into fall in temperature for hot water is equal to mass into specific heat capacity into rise in temperature for the cold water. Since both the specific heat capacities are same, substance being the same, we can cancel C from both the sides, leaving the relation mass into fall in temperature of hot water is equal to mass into rise in temperature for cold water. So this is the first case. The second case is when a beaker is containing cold water and instead of hot water, you are dropping a hot metal, a metallic ball. So in this case, heat transfer is from hot metallic ball to the cold water. So we have principle of calorimetry as mass into specific heat capacity into rise in temperature of cold water that is contained in the beaker is equal to mass into specific heat capacity into fall in temperature for the metallic ball. This becomes the second set of numericals. First one, hot water, cold water. Second one, hot metal and cold water. But in this case, both these cases we see that the container that is containing water is a non-conducting medium, that is a glass beaker. The third and fourth categories work out with the container being a conducting substance. So when we have both these conditions applied to a container that contains the substance which is a conducting substance. Say for example, we are having a copper calorimeter. Copper is a very good conductor of heat. So we are having cold water that is there in copper calorimeter, which is cold, and we are adding hot water to it. So this becomes a third condition now. Cold water is contained in a copper calorimeter. So what is the temperature of the calorimeter? Yes, definitely the temperature of the calorimeter would be same as the temperature of cold water, because cold water is contained in it. Similarly, hot water has been added to it. So we have the relation over here as applying principle of calorimetry, heat lost by hot water is equal to heat gained by cold water plus heat gained by copper calorimeter. Why? Because copper calorimeter will take part in the heat transfer, it being a conducting substance. So we have mass into specific heat capacity into fall in temperature of hot water is equal to mass into specific heat capacity into rise in temperature of cold water plus mass into specific heat capacity into rise in temperature of copper calorimeter. So here one more quantity is being added towards the cold part. Talking about the fourth case, again we have a copper calorimeter which is containing cold water, and instead of hot water we are adding a metallic ball which is at a higher temperature, which is similar to the second case that we did except for the container change. Here again, by applying principle of calorimetry, you will have mass into specific heat capacity into fall in temperature of hot metal is equal to mass into specific heat capacity into rise in temperature of cold water plus mass into specific heat capacity into rise in temperature of copper calorimeter. So basically we divide the numericals based on principle of calorimetry into these four categories. You do not get any other type as far as POC is concerned. That's principle of calorimetry. After learning what is principle of calorimetry, we go to the second set of calorimetry, wherein we talk about the change of physical state. Physical state of substance, we know that these substances are basically divided into three physical states: solid, liquid, gases. Let's consider the flow chart. When solid is converted into liquid, which is the process that takes place? Melting. Yes, melting is the process that takes place when a solid is getting converted into the liquid state. There is another name for such similar process. There is another name for a similar process which is called as fusion. So two processes take place when solid is getting converted into the liquid state: melting as well as fusion. As far as liquid to gaseous state, which are the processes that take place? There are three processes that take place when a liquid is getting converted into the gaseous state. First one, boiling. True. Second one, evaporation. Very true. And third one, vaporization. Excellent. So we know that there are three processes that take place when liquid is getting converted into the gaseous state. But then what is the basic difference between all these three processes put together? I know for sure you know differences between two processes put together. But there is one unique difference between all three processes put together. Can we guess it? Well, the difference between evaporation, boiling and vaporization is, in case of evaporation, the vapor pressure is less than atmospheric pressure. In case of boiling, vapor pressure equals atmospheric pressure. And in case of vaporization, vapor pressure exceeds atmospheric pressure. This is the only unique difference between all three processes put together. Let's go from gaseous state to the liquid state. When a gas is getting converted into a liquid state, the process is called as condensation. Yes. Or it is also called as liquefaction. So we have two processes that take place when a gas is getting converted into a liquid state. The process that we studied were condensation and liquefaction. Similarly, when a liquid is getting converted into the solid state, what is the process called as? Yes, freezing. We see water freezes to ice at its freezing point. It is also called as solidification. So two processes arise when a liquid is getting converted into the solid state: freezing and solidification. But there is one more specific case wherein we see that solid gets converted into the gaseous state without passing through the intermediate liquid state. This particular thing happens in the process which is called as sublimation. Yes. So sublimation is a process wherein we see that the solid gets converted into the gaseous state without passing through the intermediate liquid state. A very good example for this is naphthalene balls. We see that naphthalene balls are kept across various containers and chests so that it gives you a proper aroma or a fragrance. What happens in this case? It doesn't get converted into the liquid state. It immediately gets converted into the gaseous state, which process is known as sublimation.